Okay, as mentioned, a radical is simply a square root sign or anything under the square root sign. You could have something like, if I actually draw here and I say, well, the root of 9. Well, the root of 9 is in radical form. Of course, you can simplify root of 9, and we know the root of 9 is actually 3. Same thing with the root of 16. That's going to be actually 4. So you can go through. These are what are called perfect squares because if I go 3 times 3, I get 9. In other words, 3 squared is 9. That's why 9 is a perfect square, because it comes from the same thing multiplied by itself. 16 is 1. 25 is 1 because it's 5 squared. 36 is 1 because it's 6 squared, and so on. So you end up getting these ones here. Now, of course, we should always reduce our answer to either 3 or 4 and not leave it like this when it can be reduced. But sometimes it can't. And let me show you some examples here where it becomes a little bit more awkward. And things like root 48. So suppose I did an answer and I got root 48. I don't want to leave it like this because it can be reduced a little bit further. And I have to look at 48 and say, well, what numbers go into 48? Now, I got a variety to choose from here. I'm going to look at this and say, well, I think the number 4 goes in there. And the number 4 goes in there 12 times. So in other words, instead of writing 48, I'm going to write this as under the square root 4 times 12, which is the same thing. Instead of writing 48, I'm writing 4 times 12. Now I look at this and say, well, wait a minute, what numbers go into this? Well, I look at 4, and the number 4, if I look at square root of 4, that actually is 2. And so if I pull this 4 out, now there's the square root of 4 is the same thing as writing 2. So in other words, I'm going to pull this 4 right here out, and I'm going to write that as 2 square root of 12. Okay, so I've pulled this 4 out, and when I do that, the square root of 4 is the same thing as just writing 2. So that's what this is. It's the same thing as this guy. Now I still got this root of 12 here. And so in order to fight that one, I can break this up even further, and perhaps I can write that, I'm just going to write that down here, as 2 times, instead of 12, I'm going to write that as 3 times 4. Now I'll see something interesting happening here, is that I got another root of 4, which I know as 2. And so I'm going to pull that one out again, and I'm going to get 2, which comes from this one, times 2. And where this extra 2 comes from is from here. It's from the root of 4. And of course, that's all multiplied by the root of 3. Now in doing so, I get 2 times root 3. I can't multiply a radical and a whole number together, but I can multiply the 2's together, in which case I'm going to get, well, 2 times 2 is 4 root 3. And so that actually is my final reduced answer of the square root of 48. It becomes 4 root 3. You can try this with other numbers. I'll try something here. And suppose I did the exact same thing again, but I picked different ones to start off with. Last time I picked 4 times 12. This time I'm going to pick something different. In fact, I'm going to write this as the root, and actually I'm going to write 16 times 3. So 16 times 3 is the same as 48. Now the nice thing about this number is 16 is a perfect square. It's 4 squared. And so in which case I can pull that out, and I'm going to get here, that's the same as 4 root 3. And you'll notice that is exactly the same thing as we had last time when I started off with 12 times 4. It works out all to, it should all be reduced to the exact same answer. Now it doesn't matter which path you take, you should always get the same answer. Now that's to reduce radicals. And you may get something like this. It's a little more complicated. Perhaps you have to reduce something that's already partially reduced, and maybe something like 3 root 50. Again, the 3 is fine, but I just don't like this root 50 because I can reduce that a little more. I'm going to call that 3 times, instead of 50, perhaps I can call that 5 times 10. And I notice that the 5 can't be reduced anymore, but the 10 can. And I'm going to keep going with this and say 3 times 5 times 2 times 5. And now when I do this one here, 5 times 10, so this is 5 times 2 times 5, which is the same as 50. But now I get 2 5's in here. Now I notice that this is in fact the same thing as writing 3 times, well, 5 times 5 is 5 squared. 5 times 5 is 5 squared, and then I got this 2 left over times 2. Well, the square root of 5 squared is just 5. So in fact, this just becomes 3 times 5 square root of 2. And this actually can be taken out, or pardon me, combined. The 3 times 5 can just become 15 root 2. So radicals can be a little complicated when trying to simplify them. But that is 3 root 50 gets reduced down to 15 root 2, because I cannot reduce this radical anymore. One last thing is, if you ever get fractions with radicals, you shouldn't have anything in the denominator, and so it should look something like this. Suppose I have a number like 3 over root 2. That's my number. I can't leave an answer like this because there's a radical in the denominator. So in order to switch that, what I do is I can multiply it by the number 1. Whenever you multiply something by the number 1, it doesn't change the answer. And so I'm not going to multiply by what looks like the number 1, but I'm going to multiply by root 2 over root 2, which is the number 1. The reason I chose root 2 is because that's what's on the denominator. And what happens is, at the top I get 3 root 2, and on the bottom, well, root 2 times root 2, sorry, this should be times, root 2 times root 2 ends up being 2. And so 3 over root 2 actually ends up being 3 root 2 over 2. That's a better way of writing this. You don't want to leave it as 3 root over root 2. You can do another example here. You can do like 5 over root 3. And in order to do this, I'm going to multiply by, you probably guessed it, root 3 over root 3. And when I do that, I end up getting, well, 5 times root 3 is 5 root 3. And root 3 times root 3 is 3. And so 5 over root 3 becomes 5 root 3 over 3. And you can keep trying this, and this is called rationalizing the denominator.